Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 11th, 2025, about 5 days ago. The striking result is that this paper replaces traditional normalization layers in transformers with a simple pointwise function called dynamic ERF, or Derf, and still improves performance. For example, boosting VIT base accuracy from 82.3% with layer norm to 82.8%. The paper is titled Stronger Normalization-Free Transformers, and as we will see later, the implications for how we design and train deep models are quite significant. So after that overview, Figure 1 lays out the core idea visually. The top left cartoon shows a standard transformer block where the norm layer is swapped for a pointwise function, meaning each value is remapped independently. The top right panel plots many such functions and highlights dynamic ERF as a smooth S-shaped curve. Along the bottom, the diagrams contrast how layer norm, dynamic tan, and dynamic ERF act on channels and tokens, and the table reports that dynamic ERF gives the best vision, diffusion, and DNA modeling scores. So while Figure 1 showed that dynamic ERF works well in practice, Figure 2 shows why by visualizing 4 key shape properties of pointwise functions. The leftmost panel contrasts zero-centered functions, whose blue curve sits symmetrically around 0 with a shifted red curve. The second panel illustrates boundedness, where the blue curve flattens at finite limits, but the red one keeps growing. The third panel depicts center sensitivity, so the blue curve responds steeply near 0, while the red curve is flatter. The rightmost panel highlights monotonicity, with the blue curve always increasing, and the red curve bending back on itself, which can destabilize training. So while Figure 2 clarified the 4 desirable properties, Table 1 puts zero-centeredness to the test in VIT base. The table shows that small horizontal shifts up to about 0.5 keep accuracy near the unshifted case. Larger shifts, and especially vertical shifts, steadily reduce accuracy and often cause training failure. The pattern holds for ERF, TON, and ArcTAN, which strongly supports zero-centered outputs as a stability requirement. So while Table 1 stressed the need for zero-centered outputs, Table 3 probes how important boundedness is. The top row with no modification gives the best accuracies around 82 to 83% for all 4 functions. As the lambda b parameter grows and the functions become less bounded, accuracy steadily drops. At lambda b equals 0.5, training collapses entirely. The pattern shows that keeping these pointwise functions bounded is crucial for stable and accurate VIT-based training. Table 5 turns to center sensitivity, which they control by adding a flat region around 0 with width lambda. The first column, with lambda equal to 0, meaning no flat zone, gives the best accuracies for ERF, TON, and ArcTAN around 82 to 83%. As lambda grows from 0.1 to 2.0, accuracy steadily declines for all 3 functions. At lambda equal to 3.0, training fails completely, so strong responsiveness near 0 clearly matters for stable VIT-based training. Alright. After Table 5 emphasized center sensitivity, Table 6 tests the last property, monotonicity, on VIT base. The left half lists monotonic functions like ERF, TON, and ArcTAN, all reaching about 82 to 83% accuracy, and their negated versions match them closely. The right half presents non-monotonic options such as sine and the damped variants, which drop to around 81%. These results show that monotonic functions, whether increasing or decreasing, give more reliable and higher performance than hump-shaped or oscillating ones. Alright, Table 7 gathers the head-to-head comparison of many candidate pointwise functions against layer norm. The table shows that the error function rho reaches the highest VIT-based top 1 accuracy, about 82.8%, slightly above layer norm. The same error function also delivers the best diffusion scores, with the lowest Fréchet inception distance across both dTB over 4 and dTL over 4. These results confirm that the error function shape is consistently superior across both classification and image generation. So the big message is that carefully designed pointwise functions, like dynamic ERF, can fully replace normalization layers and even boost accuracy, as long as they stay zero-centered, bounded, sensitive near 0, and monotonic. That opens the door to simpler, more hardware-friendly transformers. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.